First of all, try to understand what is Van't Hoff factor. By using Van't Hoff factor, colligative properties of an electrolyte can be expressed in the relation to that of non-electrolyte. Mathematically, you can say Van't Hoff factor is the ratio of colligative property of an electrolytic solution to the colligative property of non-electrolytic solution of the same concentration. Electrolytic solution has the tendency to either get dissociate or associate. But non-electrolytic solution neither get dissociate or associate. So we can get the another formula I is equal to number of ions after dissociation or association. Here we have counted the number of ions after dissociation or association. So that's why it is equal to the colligative property of electrolytic solution. And in the denominator we have used the number of ions before dissociation or association. That means it represents non-electrolytic solution. As we just have discussed, electrolytic solution either get dissociate or associate. That means the Van't Hoff factor will be different for dissociation and for association. First of all, we are going to discuss Van't Hoff factor for dissociation. In case of complete dissociation, Van't Hoff factor will be more than 1 and it can be equal to the number of ions produced after complete dissociation. For example, if NaCl, it dissociates into Na plus ion and Cl negative ion. And at the beginning, there will be 1 mole of NaCl and there will be 0 moles of Na plus ion and 0 moles of Cl negative ion. But after complete dissociation, all 1 mole will get dissociate into Na plus and Cl negative. So finally, you will get 0 moles of NaCl because all the moles will get dissociate into Na plus and Cl negative ion. By the dissociation of 1 mole of NaCl, you will get 1 mole of Na plus ion and 1 mole of Cl negative ion. And Van't Hoff factor I is equal to the number of ions after dissociation divided by number of ions before dissociation. So after dissociation, here you will get 1 plus 1 is equal to 2. So here I have written 2. Number of ions before dissociation. So at the beginning, there was just 1 mole of NaCl. So number of ions before dissociation was 1. So I will be equal to 2. Now let's take another example. In case of FeCl3, initially there will be 1 mole of FeCl3 and 0 moles of Fe3 plus ion and 0 moles of Cl negative ion. But after dissociation, all 1 mole of FeCl3 will get dissociate into Fe3 plus ion and 3 Cl negative ion. So finally, you will get 0 moles of FeCl3 but 1 mole of Fe3 plus ion and there will be 3 moles of Cl negative. Total number of ions after dissociation will be 1 plus 3. So here you will get I is equal to number of ions after dissociation is equal to 4 and before dissociation there is just 1 mole of FeCl3. So the I value will be equal to 4 which is equal to the number of ions produced after dissociation. Now come to the Van't Hoff factor for association. In case of complete association, Van't Hoff factor will be less than 1. It can be equal to the number of ions produced after association. For example, there are 2 moles of acetic acid and after association, they both combine to form dimer of acetic acid. So at the beginning, there were 2 moles of acetic acid and 0 moles of dimer of acetic acid. But after complete association, both the moles of acetic acid dimerize to form 1 mole of dimer of acetic acid. Now apply the formula for Van't Hoff factor. I will be equal to number of ions after association because here we are discussing association divided by number of ions before association. So after association, 1 mole of dimer of acetic acid is produced. And before association, there were 2 moles of acetic acid. So here you will get I is equal to 1 by 2. Now come to the relation between Van't Hoff factor and colligative property. We know colligative property depends on the number of particles, not on the nature of particles dissolved. We know colligative properties depends on the number of particles, not on the nature of particles dissolved. Or you can say colligative property will be directly proportional to the number of solute particles. And we also know Van't Hoff factor I is equal to the number of ions after dissociation or association divided by number of ions before dissociation or association. For example, if we take 1 mole of NaCl, so theoretically we have taken just 1 mole of NaCl, but on dissolving it in water, it dissociates into Na plus ion and Cl negative ion. So when you count the number of ions after dissociation, so you will get 1 plus 1 means there are 2 moles of solute particles. Number of ions after dissociation will be the observed number of ions, and number of ions before dissociation will be the theoretical number of ions. As we know, colligative property is directly proportional to the number of solute particles. So the observed number of ions will be directly proportional to the observed value of colligative property, and theoretical number of ions will represent the theoretical value of colligative property. Theoretical colligative property is the colligative property of non-electrolytic solution of the same concentration as that of electrolytic solution. Because the theoretical value of colligative property is calculated from the theoretical number of ions, and theoretical number of ions were calculated by the number of ions before dissociation or association. Because non-electrolyte remain in molecular state, they neither get dissociate or associate in the solution. We already have the formula I is equal to colligative property of electrolytic solution divided by colligative property of non-electrolytic solution of the same concentration. Van't Hoff factor is defined as the ratio of observed colligative property produced by the given concentration of electrolyte solution to the property observed for the same concentration of non-electrolytic solution. Means I is equal to observed colligative property of electrolytic solution divided by observed colligative property of non-electrolytic solution of same concentration. We already have the formula I is equal to observed number of ions divided by theoretical number of ions. It is also equal to the observed colligative property divided by theoretical colligative property. We know colligative property is directly proportional to the number of solute particles. Hence, it is directly proportional to the number of moles of solute particles. So we can write Van't Hoff factor I is equal to observed colligative property divided by theoretical colligative property. As it is directly proportional to the number of solute particles, we can also write observed colligative property is directly proportional to the observed number of moles of solute, and theoretical colligative property will be directly proportional to the theoretical number of moles of solute. So you will get another formula for I. We know number of moles of solute can be calculated by given mass of solute, that is W2, divided by molar mass of solute, that is M2. And we know colligative property is directly proportional to the number of moles, and the number of moles are inversely proportional to the molar mass. From this relation we can derive another equation. So the Van't Hoff factor I will be equal to the theoretical molar mass divided by observed molar mass. That's why where there were observed number of moles, there will be theoretical value of molar mass. And where there were theoretical value of number of moles, there will be observed value of molar mass. That's why we got the formula I is equal to theoretical molar mass divided by observed molar mass. Now there is correction in every colligative property with respect to Van't Hoff factor. For elevation in boiling point, the corrected formula will be delta Tb will be equal to I into Kb into M. For osmotic pressure, pi will be equal to I into N over V multiplied by RT. For depression in freezing point, delta Tf will be equal to I into Kf into M. And for relative lowering in vapor pressure, delta P over P1 naught will be equal to I into X2. Now let's try to solve questions based on it. Now come to the first question. Which has the highest freezing point? 1 molar glucose, 1 molar NaCl, 1 molar CaCl2 and 1 molar AlF3. For the freezing point, we have formula delta Tf is equal to Van't Hoff factor I multiplied by Kf into M. From the formula we know delta Tf, that is depression in freezing point, is directly proportional to Van't Hoff factor I. For higher value of Van't Hoff factor, there will be more depression in freezing point. As there is more depression in freezing point, there will be more drop in the freezing point of the solution. As there is more drop in the freezing point of the solution will have least freezing point. But here we have to find out which of the following has highest freezing point. For highest TF, for high TF, we have to find out the compound which has lower Van't Hoff factor. And when you examine all the options, NaCl, CaCl2 and AlF3, they all are ionic solid. As they all are ionic solid, they dissociate into ions. So the I value for them will be definitely more than 1. But glucose is a covalent compound and covalent compound do not dissociate. That's why the I value for glucose will be equal to 1. So among all the options, glucose will have the highest freezing point. And this will be the correct option. Now come to the next question. Consider 1 molar aqueous solution of the following compounds and arrange them in increasing order of elevation at boiling point. These are the options. C6H12O6, that is glucose, NaCl, MgCl2, AlCl3 and Al2SO4 whole thrice. For elevation in boiling point, we have formula delta Tb is equal to Van't Hoff factor I multiplied by Kb into M. Delta Tb is the elevation in boiling point and it is directly proportional to Van't Hoff factor I. So for higher value of Van't Hoff factor, elevation in boiling point will also be higher. And as there is more elevation in boiling point, solution will also have higher boiling point. And here we have to arrange them in increasing order of elevation in boiling point. So let's examine each option one by one. C6H12O6 is the glucose and it is covalent compound. For covalent compound, I value will be equal to 1. Next is NaCl. When it dissociates into Na plus and Cl negative. For dissociation, I value will be equal to the number of ions produced after dissociation. And as there are 2 ions produced after dissociation, I value will be equal to 2. Next is MgCl2. when it dissociates into Mg2 plus ion and 2 Cl negative ion. So the I value will be equal to 3. Now come to AlCl3. When it dissociates into Al3 plus ion and 3 Cl negative ion. So the I value will be equal to 4. And for Al2SO4 whole thrice, when it dissociates into 2 Al3 plus ion and 3 SO4 2 negative ion. So the I value will be equal to 5. Higher the I value, higher will be the boiling point. So glucose will have least boiling point and Al2SO4 whole thrice will have highest boiling point. So when you compare our answer from the given options, you will see option C will be the right option for this question. Now come to the next question. Calculate the freezing point of an aqueous solution of 10.5 grams of MgBr2 in 200 grams of water, assuming complete ionization of MgBr2. Molar mass of MgBr2 is given 184 grams per mole and Kf for water is given 1.85 Kelvin per molal. First of all, write down what is given in the question. Here solute is MgBr2 and solvent is water. Mass of solute is given 10.5 grams. So mass of solute MgBr2 is 10.5 grams. And the molar mass of the solute is given 184 grams per mole. Mass of solvent is given 200 grams. And Kf for water is given 1.85 Kelvin per molal. Here we have to assume complete ionization of MgBr2. So let's calculate I value for MgBr2. When MgBr2 dissociate, it will dissociate into Mg2 plus ion and 2 Br negative ion. So before dissociation there was just 1 mole of MgBr2 and after dissociation we will get 1 mole of Mg2 plus ion and 2 moles of Br negative ion. For the calculation of Van't Hoff factor we have formula number of moles after dissociation over number of moles before dissociation. So after dissociation you get 1 plus 2 is equal to 3 and before dissociation there was just 1 mole of MgBr2. So the I value will be equal to 3. If there is complete ionization, you can directly calculate the I value by just calculating the number of ions produced after dissociation. So we just had calculated I value that is equal to 3. Now we have to calculate freezing point of the aqueous solution. For the freezing point we have formula delta Tf is equal to I Kf into M. When you expand the term M, you will get another formula delta Tf is equal to I into Kf multiplied by W2 multiplied by 1000 gram per kg divided by M2 into W1. W2 is the mass of solute. So here W2 is given 10.5 grams. M2 is the molar mass of the solute and it is given 184 grams per mole. Mass of solvent is W1 which is given 200 grams and Kf for water is given 1.85 Kelvin per molal. So first of all calculate the value of M by placing values in this part of the formula. So here you will get M will be equal to W2 that is 10.5 grams multiplied by 1000 grams per kg divided by 184 grams per mole multiplied by 200 grams. So here this gram and this gram will get cancelled out. This gram and this gram will get cancelled out. Here we can cancel out these two zeros with these two zeros. And 2 ones are 2 and 2 fives are 10. When you calculate it, you will get 52.5 divided by 184 molal, or you can also write mole per kg. So now we have calculated the value of M. Now place this value of M in this formula. So here you will get delta TF is equal to 3, that is the value of I we just have calculated, multiply by 1.85 Kelvin per molar, which is given in the question, multiply by the value of M, which is 52.5 divided by 184 molar. Here this molar and per molar will get cancelled out. Now convert this 184 into scientific notation. So here you will get 3 into 1.85 Kelvin multiplied by 52.5 divided by 1.84 into 10 raised to 2. So here we can cancel out 1.85 with 1.84. When you multiply 3 and 52.5, you will get 157 divided by 10 raised to 2. When you calculate it, you will get 1.57 Kelvin. So here we have calculated delta TF, but we have to calculate freezing point of aqueous solution. That means we have to calculate TF. So we need to expand the term delta TF. So when you expand the term delta TF, you will get delta TF is equal to TF naught minus TF. Here solvent is water, and we know freezing point of water is 273.15 Kelvin. So when you place the value of TF naught, you will get 1.57 Kelvin is equal to 273.15 Kelvin minus TF. When you rearrange this equation to get the value of TF, you will get TF is equal to 273.15 Kelvin minus 1.57 Kelvin. When you subtract these values, you will get TF is equal to 271.58 Kelvin. And this is the answer for our question. Now come to the next question. Determine the osmotic pressure of a solution prepared by dissolving 25 milligrams of K2SO4 in 2 liters of water at 25 degrees centigrade, assuming that it is completely dissociated. So first of all, note down what is given in the question. Mass of solute, that is K2SO4, is given 25 milligram. And the molar mass of K2SO4 is given 174 grams per mole. But the mass of solute is given in milligram and the molar mass is given in gram. So first of all, we have to convert milligrams into grams. And we know 1 milligram is equal to 10 raised to minus 3 grams. So when you convert 25 milligrams into gram, you will get 25 into 10 raised to minus 3 grams. And the volume of solution is given 2 liter. Here we have to assume complete dissociation of K2SO4. So first of all, calculate the I value for K2SO4. K2SO4 will dissociate into 2 K plus ion and 1 SO4 2 negative ion. Before dissociation, there was just 1 mole of K2SO4, and after dissociation, 2 moles of K plus ion and 1 mole of sulfate ion are produced. So the I value will be equal to 3. So that's how we just have calculated I is equal to 3 for K2SO4. And here we have to calculate osmotic pressure. For osmotic pressure calculation, we have formula pi is equal to I N over V multiplied by RT, where pi is the osmotic pressure, N is the number of moles of solute, R is the gas constant and its value is 0.0821 liter atmosphere per Kelvin per mole. V is the volume of solvent that is given 2 liter. T is the temperature in Kelvin. Here temperature is given 25 degrees centigrade. So first of all, convert degree centigrade into Kelvin by adding 273. So here you will get 298 Kelvin. So let's calculate number of moles of solute, which is not given in the question. But we can calculate number of moles of solute by using formula Given mass divided by molar mass. Given mass is 25 milligram and the molar mass is 174 grams per mole. So let's place the value in this formula to calculate number of moles of solute. So here you will get 25 into 10 raised to minus 3 grams divided by 174 grams per mole. Now place the value of N in the given equation to calculate osmotic pressure pi. I we just have calculated and it is equal to 3. So here you will get pi is equal to 3 multiplied by value of number of moles multiply by 2 liter, that is the volume of solution, multiply by the value of R, that is equal to 0.0821 liter atmosphere per Kelvin per mole, multiply by temperature, that is 298 Kelvin. Now let's solve this equation. First of all, cancel all the unit terms. Here liter will get cancelled out with liter, gram will get cancelled out with grams, per mole and per mole will get cancelled out, and Kelvin will get cancelled out with per Kelvin. Now convert this 0.0821 into scientific notation for the ease of calculation. So here you will get pi is equal to 3 into 25 into 10 raised to minus 3 divided by 174 multiplied by 2 multiplied by 8.2 into 10 raised to minus 2 atmosphere multiplied by 298. Now simplify this equation. So here 3 ones are 3 and here you will get 58. When you cancel out 2, here you will get 149. When you multiply 10 raised to minus 3 and 10 raised to minus 2, you will get 10 raised to minus 5. So here you will get 25 into 10 raised to minus 5 multiplied by 8.2 into 149 divided by 58. Now divide 149 by 58. So here approximately you will get 2.5. When you multiply 25 and 2.5, you will get 62.5. And when you multiply 62.5 by 8.2, you will get 512.5 into 10 raised to minus 5 atmosphere. When you simplify it, you will get 5.1 into 10 raised to minus 3 atmosphere. And this is the answer for our question. Now come to the next question. A 1 molal aqueous solution of trichloroacetic acid is heated to its boiling point. The solution has boiling point of 100.18 degrees centigrade. Determine the Van't Hoff factor for trichloroacetic acid. Kb for water is given 0.512 Kelvin kg per mole. Now let's note down what is given in the question. Molality of the solution is given 1 molal. Boiling point of solution, that is Tb, is given 100.18 degrees centigrade. But first of all we have to convert degrees centigrade into Kelvin by adding 273. So here you will get Tb will be equal to 373.18 Kelvin. Kb of water is given 0.512 Kelvin kg per mole. And we have to calculate Van't Hoff factor I. So we can use elevation in boiling point. For elevation in boiling point, we have formula delta Tb is equal to I Kb into M. M is given, Kb is also given, and we have to calculate I. But delta Tb is not given in the question. For the calculation of delta Tb, we have the formula delta Tb is equal to Tb minus Tb naught. As the solution is aqueous solution, that means the solvent used is water. and the boiling point of water is 373 Kelvin. Now we can calculate delta TB. TB is given 373.18 Kelvin and TB naught we know it is 373 Kelvin. So when you subtract it, you will get delta TB is equal to 0.18 Kelvin. Now place the value in the given formula, that is delta TB is equal to I Kb into M. So when you place the value of delta TB, you will get 0.18 Kelvin is equal to I multiplied by Kb, that is given 0.512 Kelvin kg per mole multiplied by 1 mole per kg. For molality, other unit is mole per kg. So either we can use molal or we can use mole per kg. So here per kg and kg will get cancelled out. Per mole and mole will get cancelled out. And Kelvin will get cancelled out. So when you rearrange this equation to calculate the value of I, you will get I is equal to 0.18 divided by 0.512. Now convert these values into scientific notation for the ease of calculation. So here you will get I will be equal to 1.8 into 10 raised to minus 1 divided by 5.1 into 10 raised to minus 1. So 10 raised to minus 1 and 10 raised to minus 1 will get cancelled out. And when you simplify this term, you will get I is equal to 0.35. And this is the answer for our question.